My name is Peggy. I'm from UNSW and also ARC Center of Excellence in Fleet. And today I'm going to introduce how we use the ANFF facilities help us with studies on the ferroelectric topological defect-based low energy electronic devices. So our group is led by Professor Nagarajan Vananu in UNSW, and our main research are focused on the multiferric nanomaterials. And about our researches, one of the very important factor, one of very important thing for us is to fabricate the high quality top electrode or the devices for us to characterize these ferroelectric materials and to study its device function. So we used the ANFF facilities like e-beam lithography, photolithography, and small evaporator, and the PVD to prepare like various kind of devices like in micron size or in the nanoscale size. So this will help us like for all those studies. And the topologic defect I introduced in my topic is very like a new idea recently found in this, has been studied intensively in this ultra-thin ferroelectric materials. And this is a type of ectotic ferroelectric domains, which this kind of topological domain features. For example, like including these different type of domain walls, vortex, and very well-known Skyrmian structures. And these topological defects in the ferroelectric nanomaterials has been found with like two very special and typical features. And one is it often has a very, very small size. So for example, in the previous studies, from the TEM, we can see that the size in superlattice is less than like 5 nanometers. And on the other hand, these kind of features also often shows emergent properties which never seen from a bulk material. So for example, the high conductivities in the core center of this vortex. So if we combine these two features of the small size and these emergent properties, it provides us like a good opportunity to develop this kind of topological defects in these materials and into some device functions. Okay, so talking about device function, then we need to design and fabricate the electrode or the devices on these materials. One of our studies a few years ago is fabricate, and we successfully realized these domain wall memory devices on the BFO thin films. And by using the e-beam lithography and also the e-beam evaporation, and we prepare these very small nanoscale size devices on this BFO. And then using the scanning probe microscope, it can help realize, we can realize it like to create and to erase these domain walls, which is conductive in these BFO films, and to realize this, the memory functions. So these details of these studies will be given more by Dr. Daniel Sandro in the ANFF Showcase this afternoon. So if you're interested, please don't miss it. And another study we've done recently is also a device, device which shows the giant piezoelectric response in bilayer PZT films on a silicon substrate. And in these materials, we fabricated two types of electrode. One is typical like top electrodes with a square size, square shape, and another one is we made these IDE like finger shape electrodes, which for us to understand is in-plane polarization and other in-plane characteristics of these materials. So why in-plane is important is when we made this bilayer with a tetragonal PZT on top of a rhombohedral PZT, And we found that the top layer PZT is actually changing to a pseudo tetragonal. It's actually also home-based structures. And this one, according to the crystallographic structure analysis by XRD and also by TEM, we found it has very clear in-plane polarization, and also like it's actually like a tilted in-plane polarizations. And all these in-plane polarizations has been evidenced also by the piezo response force microscopy. And we can see that there are two typical domains, which is like a super domain shows clear different in-plane orientations, and inside each super domains, there are like small subdomains which gives us, show us this very typical A1, A2 domain structures. So this is very important because when we apply external bias, these very elastic A1, A2 domains will just move. And this movement of these domains can contribute to a really high electromechanical response, which I'll introduce later. And in addition to these domain wall movements, the very elastic domain wall movement, we also observe these tiny topologic defects in these films, in the as-grown films, which shown as anti-vortex and vortex structures. So this one I have shown in the beginning that in some studies it has a very clear high conductivities, which we will also do more studies on that later. And very interesting is also after applying the bias, and these topological defects also has a movement, as the motion of these topological defects could again possibly contribute to some of the high polarizations or the electromechanical response, which we have been observing in these films. So we can see if we compare to a single R-layer rhombohedral PZT or some other single layer PZT, this kind of a bilayer PZT showing the very elastic domain walls and also the topological defects, it shows a much higher electromechanical response. So it's very important for us to verify this also from a microscope like analysis. So here we just use this small electrode and the devices to analyze this polarization and capacitances. And we can find that both in-plane polarizations and the capacitance shows a much stronger signal compared with this out-of-plane measurement. So all these are attributed to its in-plane polarizations from this crystallographic structure analysis. So this is one of another case of how we use the ANFF facilities to prepare all these devices to help us for these characterizations and for us to understand more of our materials. And in future, one of our plan is to keep working and explore the devices and how to design the fabricated devices for another topologic defects, which we call the nanoscale bubble domains. So these domains shows a very small size, which is less than 10 or 5 nanometers from the from the piezo response force microscopy. And also we found that these domains also shows a high conductivities compared to the neighboring areas according to the conductive AFM. So that also means that if we have a chance to design devices, we like make devices, we can probably realize some memory functions based on this material. And also, in addition, in our lab, we have also did some studies to understand the transitions based on the configuration of the film by fabricating, by design fabricating this material and to tuning the deposition process. So yeah, this is another like project who probably will just focus to like develop its device functions. So here is here is all the project I just showing that how the ANFF facilities help us with our studies, and I would like to thank all our like group members on these projects and our collaborators. Yeah, thank you very much.